3.4 Mixture. Mixture refers to the type of problems when we mix things with different temperatures together. For example, when we mix hot water with cold water, then there will be heat exchange between them. The hot water gives out heat and the cold water absorbs it. The temperature of the hot water drops and the temperature of the cold water rises, so that their final temperature becomes the same. Similarly, when you put a piece of hot metal into cold water, the hot metal will give out heat to the cold water, so that their final temperature will be the same. And so we may apply that equation below. The heat loss by hot object equals to the heat gain by the cold object. And the heat loss by the hot object, which is the metal piece, will be equal to mc delta T, where delta T is the change in temperature. Since the hot metal has a higher temperature than the final temperature, in this way we may find the change in temperature by Tm, that is the metal temperature, minus Tf, that is the final temperature. And that energy will be absorbed by the cold object, and in that case, the cold water. So it is mc delta T again, m for the mass of water, c for the specific capacity of water, and lastly, change in temperature, represented by Tf minus Tw. You may notice that on the equation, on the left hand side, it is Tm minus Tf, so to give a positive temperature change, while on the right hand side it is Tf minus Tw, also to give a positive temperature change. And what about the heat absorbed by the cold water container? So that will be expressed as C delta T, where C is the heat capacity of the cold container, and delta T is the change of temperature. So if it was the container for the cold water, then the change in temperature would also be equal to Tf minus Tw again. And what follows will be a video of the experiment of mixing water of different temperatures. So find out one precaution of the experiment and explain the precaution.
Half fill one polystyrene cup with cold water and another cup with hot water. Measure the mass and temperature of the water in the two cups. Quickly pour the water in both cups into another cup. Stir the mixture and read the new temperature.
So, any idea about the precaution of the experiment? The answer is, we should do the experiment as fast as possible, so as to reduce the heat loss to the surroundings. Otherwise, there will be a lot of heat lost to the surroundings, and so the heat loss by the hot object may not equal to the heat gain by the cold object. By the way, in the above video, we did not calculate the heat gain or heat loss by the formed curves. So the calculated final temperature will be higher than the experimental value. Now please copy that down. Now an example on the next page. Now we have 0.5 kg of water at 80 degrees Celsius mixed with 0.2 kg of water at 20 degrees Celsius, and we are going to find the final temperature. So we have all the values M1, T1, M2, T2, as well as the specific capacity, and they are all the same, 4,200 joule per kilogram per degree Celsius. And then the heat loss by the hot water, M1C1 delta T. And the heat gain by the cold water, M2C2 delta T dash, where delta T is T1 minus T3 and delta T dash T3 minus T2. You should always remember T3 is in between T1 and T2 when you try to express the two change in temperature on the two sides. And this is to say the final temperature X is something in between 80 and 20. And now I'm sure you may know how to write the equation below. You may notice that we have neglected the heat gain and heat loss by the foam cups again, because the heat capacity of foam cups are usually very small, so their heat gain or heat loss are also very small. So it will be okay to neglect it. Now, would you please use a calculator to calculate the final temperature X in this question and check your answers before you move on. Question 88 is pretty much the same, and this time there is a piece of copper, 0.15 kilogram, at a temperature of 90 degrees Celsius, and it is put into 2 kilogram of water at 20 degrees Celsius. So again, the cold water is going to absorb energy, while the hot metal is going to release energy. So you may find the heat loss by the hot metal, Q1, expressed as mc delta T, and similarly the heat gain by the cold water, mc delta T again. You may refer to the table on the right hand side to find the specific capacity of copper to be only 400, while that of water is 4200. There is an assumption for that kind of question. There is always assumed to be no heat exchange with the surroundings, even including the foam cups. Now would you write the equation for question 88 and finish it and try to find the final temperature yourself. For the last part of the video, let's take a look at question 89. You can see there is water. There is also a container with a heat capacity. And lastly, there is also another cup of water mixed together. So you have hot water, cold water, also a hot container. We are going to find the final temperature. Let's do it together. First, we assume there's no heat exchange with the surroundings. And then there's now heat loss by the hot water, and also heat loss by the hot container. And in this case, you should note that the initial temperature of the hot container is also 60 degrees Celsius. And then the energy will be absorbed by the cold water, which is 2 times 4200 times bracket T minus 20. By the way, you should know that the final temperature T is somewhat in between 60 and 20. Maybe it is 30 something, 40 something, 50 something. So you should have temperature change on the right hand side here to be T minus 20, while this is 60 minus T on the left hand side. And one more thing is about this expression. This is heat capacity multiplied with temperature change for the container, while for water it is mc delta T. mc delta T for the cold water as well. And now you should be able to calculate the final temperature, capital letter T, yourself. Now finish the last two Questions before you attend the next physics class.